Right, ladies and gentlemen, welcome. My name is Dejan Hanzalek, and you are watching the 57th talk of the scheduling seminar. Let me ask Dvir Shabtai to introduce the speaker.
Hello, it is a great pleasure to present Dr. Professor Matthias Mnich from TU Hamburg as our speaker for today. Professor Mnich holds a master's degree in applied mathematics from London School of Economics and Political Science. He earned his PhD degree in 2010 from Eindhoven University. His advisor was late Professor Gerard Wugegner. He did his postdoc at Berkeley International Computer Science Institute. His advisor was Richard Sharp. Okay, so he was among the most famous advisors in the field. He then held several different positions as researchers and professor in several universities. Currently, Matthias served as the head of the Institute for Algorithms and Complexity at TU Hamburg. Matthias' main research topics include parameterized complexity in algorithmic design. He's among the first researchers to analyze the parameterized tractability of scheduling problem, to apply this theory in scheduling. And I would like to mention two of his papers that highly affect the community, I believe. The first is Scheduling and Fixed Parameterized Tractability, published in Math Programming in 2015. And the second is Parameterized Complexity of Machine Scheduling, 15 open problems published in Computers and Operation Research. I believe that since then, few of them already solved, and 11 are left open, as I understand. Matthias, the stage is yours.
Yeah, thank you, Dvir, for the kind introduction, and also thank you very much to the organizers for allowing me to present my work here. So this work is a joint work with Sebastian Bernd from the University of Lübeck and Hauke Brinkop and Klaus Jansen from the Kiel University and Tobias Stamm also from Hamburg. So it's a collaboration here from the north, and what I would like to talk about concerns classical problem, Makespan minimization on uniformly related machines, but it also the techniques can hopefully also be used for several other scheduling problems and even optimization problems beyond scheduling. So let me introduce the problem. So this problem in classical scheduling notation is written as Cmax. So what is Cmax in Graham's notation? We are given a set of jobs, and each job essentially is characterized by an integer. And the integer is the processing time, or the time it takes to process the job. So we have n of them, and then we also have a set of m machines. So in these machines, they have speeds. Processing speeds. The speeds can be arbitrary integers. And here we see 3 machines, and their speeds are 1, 2, and 3. What we would like to compute is a schedule. A schedule is simply an assignment of jobs to the machines. So, and we want to assign the jobs to the machines in such a way that the so-called makespan is minimized, which we denote here by opt. So what is the makespan? It is the time by which the machine that finishes last completes the processing of all the jobs. So in the example that you can see here on the slide, we have a makespan of 3. So why is that? Well, if you add up the processing times of P2 and P5, then we have then this is 6. However, this machine runs at the speed of 2. So therefore, processing these jobs of processing time 6 takes only 3 units of time. And likewise for the machine 3. So therefore, we can find an assignment of jobs to the machines so that the makespan is 3. So it is well known that this problem, denoted by Cmax, is NP hard. So therefore, finding schedules that find the optimal packing is likely to be obtainable in polynomial time, and we therefore settle for computing a 1 plus epsilon approximation. So we want to find a schedule where we violate this optimal Makespan only by a 1 plus epsilon factor. And these schedules we want to find as quickly as possible. So here's an application for this problem. Suppose you attend a conference, like one of the scheduling conferences like MAPS or Euro, and then at some point of the conference, at some evening, there will be a conference banquet. So everybody's sitting at the tables and the waiters are serving the food. And naturally, the waiters have different speeds at which they operate. Some are senior waiters, some are just apprentices who still need to learn how to work faster, serve faster. And then the dinner can only start once everybody has been served their food. Yeah, so serving different people takes different time because they sit in different locations of the room. And so if we have some good scheduling algorithm, then, and we know the speeds by which the servers or the waiters are operating, then we can assign them the duties who should serve whom, so that the conference dinner can start as quickly as possible. So this important application motivates designing algorithms for this problem. And one particular special case has been well investigated over many years now. And this is the special case when all the machines have the same speed or when all the waiters operate at the same speed. So this special case is known as PCMax. And for PCMax, the fastest known algorithm dates from 2018, and it computes a 1 plus epsilon approximate schedule in time, which is linear, so linear in the number of jobs, and then plus some additive function that depends exponentially on 1 over epsilon. So the algorithm is by Jansen and Rohwedder and employs an ILP solver and the formulation of the problem with few constraints. This was recently improved slightly, and when I say slightly, then I mean that the log squared in the exponent was improved to a log 1 over epsilon times log 1 over epsilon. So, but if we look at the setting of Cmax, which is our problem, where we have arbitrary processing times S1 up to Sm, then in 2016, again, Klaus Jansen had a paper on this problem and gave the fastest known algorithm for this problem based on an MILP. So M stands for mixed, meaning that some variables can take fractional values. And here the complexity is similar, except that log squared in the exponent, we have a log to the 4 in the exponent. Now, our new result shows that we can improve upon the log 4 in the exponent and get a log 3 times a log 1 over epsilon. Now you might say, okay, isn't this just an incremental result? Well, on the one hand, at first sight, it may seem so. However, notice that the logarithmic dependence on 1 over epsilon is in the exponent. So therefore, the speed up is more significant. That's one motivation. And the other point is that for many years, I mean, these problems are really basic. PCMax and QCMax have been studied for several decades. So it is worth investigating even for these very basic problems. We don't know yet what the exact or what the best possible runtime is to find near optimal 1 plus epsilon approximate solutions. So therefore, even a small improvement may lead to new insights that can later give better algorithms. So, and here on this slide, you can see already that for many years, for QCMax, people try to come up with faster and faster algorithms. And the first ones that obtained 1 plus epsilon approximate solutions, they still suffered from the curse of dimension, having 1 over epsilon in the exponent of n. since n is large, choosing epsilon small, this gives a practically infeasible runtime. So in 2010, it was for the first time that there was an additive separation of 1 plus epsilon, 1 over epsilon from n, the total number of jobs. So since so then the constant here in the degree was not specified, and since our goal is to have algorithms that are interesting both theoretically and practically, we also pay attention in our new result so that here we have a linear runtime to get at least for certain values of epsilon to some practical algorithms. I just want to mention that a third feat of our algorithm is even if this runtime improvement may seem incremental, one main feature of our algorithm is that it's much simpler than the previous ones. So therefore, there is also a chance to have in the future some possible implementation of it. So for the special case, notice that we are pretty close. So we are just a log squared factor away. And in the past, it has been the case that once there has been an improvement for the special case Cmax, then a few years later, such an improvement was also found for Cmax. So the hope is that our algorithm can inspire this in future work for Cmax as well. So how do we obtain this new result? Well, as I said, the algorithm is simpler as previous ones, so it operates in a few stages. First, the instance is pre-processed, so some simple observations are made to simplify the instance. And then we search not only for we do not search for the optimal Makespan, but we guess the optimal Makespan. So using binary search, we make a guess. This could be the solution value and try to find an assignment of the jobs to the machines that satisfies this Makespan or that packs within this solution value. And since there's only few values to search, we can try all of them. Given this guessed Makespan, we set up a mixed integer linear program and we test its feasibility. If the program is infeasible, then we reject and we try with a different guess for the binary search objective. Otherwise, we have found a feasible packing and we take the one for which the smallest, we take the Makespan for the smallest Makespan for which the MILP here is feasible. Given a solution, so once we found a solution for the MILP, we still have to construct a schedule. So this is the last step of the algorithm. Our key new idea, one key new idea is to use recursive configurations, where we simulate a new machine as an additional job on a faster machine. I will tell you the details in a moment. So this allows us, this key insight or key idea allows us to obtain an MILP formulation with a certain property. And this certain property is that the maximum column norm, so A is usually the constraint matrix of this MILP, and A max is the column norm. So we take the entries of one column, we add them all up and look for the maximum among all columns. This allows us to obtain a better bound on this column norm. Yeah, so the previous results had 1 over epsilon dependence here, and we are exponentially better. We have only a log 1 over epsilon dependence. So, and then when we have this, we need still one new result. And this is the result that I want to promote. That is hopefully useful for many other scheduling problems, as well as for many other optimization problems. Namely, we have a new support size bound for ILPs. So what does it mean? Usually, one can solve an ILP by relaxing it to a linear program, by dropping the integrality constraints. And then one can solve the relaxation optimally and find a solution. And if the solution has small support, meaning that only few variables take non-zero values, one can guess an assignment to them in fast time. So the smaller the support, the fewer variables take non-zero values, and we can guess the values. And here we have a new support bound. And this support bound depends only on a max, so it depends only on this largest column norm, and this should be applicable in many other optimization problems as well, which can be formulated as integer linear problems. Again, I will share the details with you in a moment. So beyond QCmax, we also look at the high multiplicity version of it. So what is the high multiplicity version? So far, I told you that we have given a set of n jobs and m machines. So, but this is not a very efficient encoding if we have a large number of jobs or a large number of machines. High multiplicity encoding means that instead of having given all the jobs and all the machines one by one, we have types of jobs. So all the types of machines, all jobs of the same type and all jobs of the same type have the same processing time. All machines of the same type have the same speed. So, and then we only need to encode how many jobs there are of a certain type and how many machines there are of a certain type, and of course their processing time or their speed. Such an encoding can be exponentially smaller than a standard encoding where we are given one job or one machine at a time. And therefore, it is exponentially harder to design efficient algorithms for them. To the best of our knowledge, there was no approximation scheme for this encoding known. And our algorithm also works for this encoding, which is very efficient and still has the same asymptotic runtime. We can further extend our result to a setting of that was studied by Jansen and Mark, where we have chi types of machines, and these machines are related through uniform speeds. Again, we get an improved runtime, so they had a log to the 5 in their runtime, and yeah, we can also improve this. So here we can save a few log factors. So now let me come to the mathematics behind this problem and how we approach it. So let me first remind you again of the problem, which is Makespan minimization on uniformly related machines. So we have given the set J of n jobs, their processing times P1 up to Pn are integers, and we have the set M of m machines, and their speeds are S1 up to Sm, which are also integers. Now, a schedule sigma assigns the jobs to the machines such that the makespan is minimized. So the makespan is this variable Cmax, and it is the maximum load over all the machines. Now, what is the load of a machine? The load of a machine is the sum of the processing times of the jobs that are assigned to the machine, so divided by the speed of the machine. So same as in the example figure that I have shown you at the beginning. Our goal is now to obtain an efficient polynomial time approximation scheme. So which is an algorithm that for any given epsilon and any instance I of the problem in time, some function, depending exponentially, likely exponentially, on 1 over epsilon plus some polynomial in the input size. So in this time, it computes a schedule whose makespan is at most 1 plus epsilon times the optimal schedule. So one can view EPTAS or efficient polynomial time approximation schemes as fixed parameter algorithms, where the parameter is the inverse of the approximation factor. And this then nicely relates to the paper that was mentioned by Dwyer, namely the parameterized complexity of scheduling, where, yeah, as Dwyer said, most of the problems are still open, and he and his co-authors resolved some of them. So let me direct you to their work, which is very interesting. So now let me explain to you the key idea, which are the recursive configurations. So classical approaches for QCmax work on one of two employing one or two linear programming relaxations. The first relaxation that has been studied is the so-called assignment LP. The assignment LP is very simple, or the idea behind it is very simple. It works as follows. Every job has to be assigned to a machine. So we can introduce variables xij which simply say, is job I assigned to machine J? So this gives us the assignment LP. On the other hand, the assignment LP is nice because it has few variables and few constraints. Unfortunately, yeah, the insight that one can get from it is not so useful for obtaining strong approximation guarantees. On the other hand, there is the configuration LP. The configuration LP has variables xi gamma, where I are the jobs and gamma are the configurations. So it's simply, what is a configuration? It says that I have a certain set of jobs on the machines, and the jobs are given by their processing time. So I say how many jobs of each processing time are given to a certain machine. And then the configuration LP tells us how many machines there are of a certain configuration. So the advantage is that this is a very compact formulation, but one can have exponentially many configurations in the number of jobs. So it's not clear how to solve this efficiently. Okay, one has to dualize, but still the number of configurations is 1 over delta, and where delta is related to the approximation factor. So this again has its disadvantages. Our recursive configurations are in the middle. Recursive configurations work like this. So first we group some jobs and we assign them to certain machines. These are the virtual machines. And then we see them as new jobs. And once we have done this, then we assign these jobs, or these machines, these virtual machines, we assign them to the final machines. So this recursive idea allows us to reduce the number of configurations from 1 over delta to log 1 over delta. Now, through this recursive step, or through this improvement here, we can reduce the number of variables in the mixed integer linear programming drastically, and therefore get over the disadvantage of the configuration LP. So when I say 1 over delta, then I want to say, so delta relates to the approximation factor, 1 over epsilon. And the nice thing is that we can allow inaccuracies in many places. So our algorithm, as I showed you, proceeds in many steps: pre-processing, guessing, solving the MILP, and so on. So in each step, we can allow some small additive violation of the optimal Makespan. So we make always a small violation, but this is not so bad because of the arithmetics. We still get something that is 1 over epsilon. So we can choose our epsilon to be, or we can choose our delta to be linear in the approximability factor, and don't disturb the approximation guarantee. Yeah, so we can add these errors up, and everything is still fine. So here's now the process. So what does the pre-processing do? It first removes some small jobs and machines. Then it does the binary search for the Makespan, as I already said. And then we do an important rounding step. So we need to round the processing time and machine speeds. Then we solve the mixed integer linear program. So we construct an MILP and find a feasible solution. And finally, we reconstruct the schedule. And here we need to round the configuration variables and assign the jobs and configurations. Why do we need to round? Well, because it's an MILP, we might obtain some variables that take fractional values. So what does the pre-processing do? So first we remove the negligibly short jobs and slow machines. Yeah? So that afterwards we have that all the processing times are at least Pmax times delta divided by n, where you recall that delta relates linearly to 1 over to epsilon, the approximation error. And same for SI. So all the machine speeds satisfy this condition. Just lower bound here on the machine speed, so they're all sufficiently fast. Then we bound the Makespan T, and perform a binary search in this range. So T is at least Pmax divided by Smax, and at most N, the total number of jobs, times Pmax divided by Smax. So the range of T here depends only on N, so there's only a linear overhead in the runtime. This is good, because it allows us faster algorithm design. So here we have a graphical interpretation of what the range of parameters is. Yeah, so in this range, we can find the optimal, we can find the Makespan, and therefore we only guess for T in this range. So I told you that at some point we need to do rounding. And why do we need to do rounding at all? So let me say that rounding is a classical means for designing these scheduling algorithms. The point is that we have an unbounded number of processing times. And we also have an unbounded number of machine speeds, unbounded in 1 over epsilon or 1 over delta. For that matter, that's the same. Now, if you have two machines that have their speeds very close to each other, or if you have two jobs that have their speeds that have their processing time very close to each other, then they should be treated the same. Yeah? So that we don't have to deal with so many different variables. So we round them. So there is classical rounding has been employed, arithmetic rounding, and it leads to a certain number of points that have to be considered. It also bounds the configurables that have to be considered in the mixed integer linear program. So this is 1 over delta squared in the previous case. One can do something better in the sense of the number of points that have to be considered. Yeah, so there can be fewer points, only log 1 over delta many. But then this comes at a price. Namely, the price is that the configuration size now depends on 1 over delta, so it is not constant anymore, and therefore the number of variables blows up considerably. Now, what we will do is we will do a mix. So we do geo-arithmetic rounding, so and this allows us to still have fewer points than the arithmetic rounding, but also fewer configurations than geometric rounding. So therefore, the number of variables here is exponentially smaller than in the geometric rounding, and okay, worse than in the arithmetic rounding, but still good enough for our purposes. Here, you can now see the configuration LP. So, the mixed integer linear program that we use, and we call this the recursive MILP because, as I explained to you, we recursively construct virtual machines by gluing some jobs together and already assigning them to some machines. And then on the jobs that we have already assigned to machines, we again assign them to new machines. So we don't have to look into the details, just that you see that there are very few constraints and very few variables, and these depend only on the number of jobs of a certain processing time and the number of machines of a certain speed. So now when I say here they depend on a certain processing time or on a certain speed, these are already the rounded speeds and rounded processing times. So therefore, the number of machines here is bounded by something that depends very nicely on 1 over delta. And here the number of different jobs or number of variables that we have to consider for the different processing time also just depends on 1 over delta. So that's a very nice dependence. Depends linearly just on 1 over delta. This is important. So, and we can solve this mixed integer linear program using known solvers, but now we need to invoke our new combinatorial bound. So there is a classical result which has already made it into various textbooks by Eisenbrand and Shmonin from 2004, namely, take any feasible integer program that is bounded, you have m constraints, and then it is guaranteed that you find a solution of small support size. In other words, you're guaranteed to find a solution where only few variables take non-zero values. You can discard all the other variables, and only for these few variables you have to guess or find out in some algorithmic way what the actual value are, what the actual values are. Now, what is this bound? Well, this is 2 times the number of variables times the logarithm of the number of variables and delta, where delta is the largest absolute value of any entry in the constraint matrix. Our new bound improves on this in a certain way. Not all the time, but in some ways. So how does it improve? So first of all, we have to restrict ourselves to integer linear programs. Then we also have M constraints. This is as before of the constraint matrix A. And now our support size is such that where we still have the dependence on M. We have a linear dependence on M, the number of variables, that doesn't change, but we only have a logarithmic dependence on A max. So A max is the column sum. Yeah, so of course it holds the relation that delta is always at most A max, but it may be that here we have a much larger value and still the dependence is the same. Yeah, so here we have a logarithmic dependence on just one value, the largest absolute value of any entry. And here we have a logarithmic dependence on the sum of all values, on many values, so M values in some column. Yeah, so and then we have here a very small additional factor, but that doesn't play a big role. So this is the main idea that we need here. And how to prove this? Well, we use we analyze the determinant of this matrix, and then we use a very nice and deep result from transcendental number theory called Siegel's lemma to obtain this new support bound here. And as I said, I believe it will have applications way beyond the Makespan minimization problem on uniformly related machines. So then we solve this MILP. For this, we use classical result by Lenstra, Cannon, and follow-up work by other people, namely that if we have a mixed integer linear program with n variables, s of which are integral, then we can solve this in time, which depends exponentially on s, so the number of integer variables, but only polynomially on the total number of variables. So the idea is now that we have an ILP, or due to the geo-arithmetic rounding that we did, our ILP, our mixed ILP has some very nice parameters. Namely, we have a total number of variables which is exponential in the logarithm square of 1 over delta. And here, as the number of integer variables depends only linearly or near linearly on 1 over delta. So, and this is the factor that eventually ends up here in the exponent and therefore yields our overall runtime. So that's how the algorithm essentially works. So eventually we have solved the MILP, we have found a feasible solution, but this is not the end. The end means that we want to come up with a schedule. So we still need to turn the MILP solution into an actual schedule that tells us how to assign the jobs to the machines. So some of the variables are fractional, so we need to make them integral. What do we do? Or how do we do this? Well, we use a vertex solution, so a special solution of the fractional part for this recursive MILP. And then for each machine speed, we have only a bounded number of positive variables and this is due to the support size bound that we have proved. We round down these variables, we lose a geometric sum, and then we also know that because of our initial rounding, where we rounded the processing times and machine speeds, we still get some, only a small additional factor on the fastest machines. And remember that we can always lose these additional small factors because they will eventually just give us an additive epsilon in the approximation factor, so that's fine. And then we recursively construct a schedule resolving the virtual machines. Yeah, because so far, remember that not all these jobs here, not all these jobs are actual jobs. So some of them are virtual because they were constructed by gluing some other jobs together at earlier levels of the recursion. So we need to repeat this a small number of times. And this number depends on the steps of the geo-arithmetic rounding. So at this point, we have constructed a schedule, and by making all the variables integral and therefore telling us how many configurations there are, which means how many machines of a certain type have how many jobs of a certain type. So, and when we have this, then it is clear that from this integral assignment, yeah, we can exactly reconstruct the schedule. So this gives us our desired result, namely, it gives us an efficient polynomial time approximation scheme, and the runtime dependence on epsilon, 1 over epsilon, is indeed better as that of previous algorithms. And here we have a runtime that is near linear. But we are not satisfied with this. Yeah, we want to have a linear dependence on the number of jobs. So how do we do this? Well, we simply construct the schedule faster from the given MILP solution. And the bottleneck that we need to overcome for this purpose is that we have to transform the MILP solution to the feasible schedule in a faster way. So, well, the idea now is to come up with a new MILP solution, MILP formulation, and we call this the hybrid MILP. And this hybrid MILP is similar to the recursive MILP in the sense that it uses both configuration and assignment variables to improve the runtime. However, yeah, it doesn't use the recursive steps. So we only solve it once, and then we directly, once we have the solution to the recursive MILP, we transform it into a solution of the hybrid MILP, which we only need to solve once, compared to that of the recursive MILP, which we need to solve several times. And since we can solve this hybrid MILP in time that is sublinear in n, we can therefore then allow, or we therefore have enough remaining time to construct a schedule from this hybrid MILP in linear time. So how does this work? So eventually, yeah, we have this solution then in the schedule in time linear in n. How does this work? As I said, the hybrid MILP is simpler. It doesn't have any recursive configurations. It's simply a mix of assignment variables and configuration variables. So configuration variables, as mentioned before, they indicate how often a configuration is used on the machine I, where a configuration specifies for each processing time how many jobs of this processing time are on the machine. For short jobs, we handle them differently. A job, we say that a job is short if its processing time is at most delta divided by Si on machine I. So recall that Si is the speed of machine I. And for these, we introduce assignment variables telling us exactly, so the variable Yij tells us exactly how many jobs of processing time Pj are assigned to machines of speed Si. Then we have 3 sets of constraints. What is the first set of constraints? It enforces that every machine is assigned some configuration. Yeah, so that's simply a matter of feasibility. We have to use the machines. We want to use the machines anyhow. So let's assign some configuration to the machine. The second set of constraints guarantees that every job is scheduled somewhere. So this is important because, well, this is the main task of the problem, and this is, corresponds to the packing constraints of the assignment IP. And finally, the third set of constraints ensures that the speed used by the short jobs is at most the speed left free by the configurations. Yeah, because now on every machine, we assign some jobs through configurations and some additional short jobs through assignments. And we need to make sure that together they fit in the guessed Makespan, yeah, so that we are not exceeding the space available on the machine. So, and then we have this recursive MILP that I told you about. And in step 1, we convert this optimal solution for the recursive MILP. Note that this recursive MILP we solve optimally, and all the variables are configuration variables. Yeah, so here we have only X variables. And we converted it into a feasible solution of the hybrid MILP. Now, the hybrid MILP, as I said, has 2 types of variables: configuration variables and assignment variables. And we don't need to have an optimal solution here. We just need to have a feasible solution with some additional properties that I don't have enough space to write here on the slide. So at the time we need for this task is here also bounded by something that is exponentially 1 over delta, and crucially sublinear in n the number of jobs. And why can we do it sublinear? It might sound surprising at the first sight, but at the second sight, well, these are just configurations. Yeah, so this can be sub-exponential indeed in the total number of jobs, because we have all the numbers in the configuration LP encoded with logarithmic many bits. In the second step, from the feasible solution of the hybrid MILP, we then construct the schedule with the Makespan in linear time, so linear in the number of jobs. So there are 3 key ideas to achieve this. First is that we round the configuration variables down and assign 1 configuration to a fastest machine for every rounded variable. So this satisfies also the first set of constraints, and because we round down, we make sure that we are not exceeding the machine capacity. Then we use basic solutions. So we have not just an arbitrary optimal solution here for the recursive MILP, but we take a basic solution. And from this, we construct a schedule, again, with small multiplicative error here, 1 plus O of delta, so that's fine. And eventually, we note that any machine of a fixed speed has at most 2 fractional assignment variables from the short jobs. So in other words, all the assignment variables, yeah, they are integral for every machine speed except for 2 of them. So, and this is nice. Yeah, so the variables can only become fractional when we run out of machine capacity. Yeah, so again, we assign some jobs to machines through configurations. So then a machine has a certain capacity left, and we assign the short jobs to it. And it may be that some short job doesn't fit on it. So this gives us a fractional variable, but it only gives us 1 fractional variable per group of jobs. And the groups are the groups that result from the geo-arithmetic round. So, and these steps taken together, they ensure that we can construct an optimal schedule in time which is linear in n, so the total number of jobs, and exponentially only in 1 over delta, where the exponential dependence on 1 over delta is better than that of all previous algorithms. And now I have given you the complete algorithm, and it's by no means trivial, but interestingly, it is still much simpler than previous algorithms, which used dynamic programming at some stage or massaging of the MILP solutions and various other tricks. And all this we can avoid. So, and the whole algorithm is also self-contained, including the combinatorial argument. The only and main external result that we are employing here is the solution, is the solving of a mixed integer linear program, for which we use the work of Lenstra, Cannon, and follow-up work. So, and finally, all the remaining jobs, we can just pack them greedily. They correspond to integer variables, and that's it. So as I said, our result extends to other settings. So for example, this setting was studied by Klaus Jansen and Mark, where we have M machines with various speeds, like in our setting. And they also have a type, so that specifies which jobs they can process, and the job set J is the same as before. But now the processing time here, Pij, depends also on the machine type. So, and then the Makespan that we want to minimize, this objective is the same as before. And the runtime, as I said, which they obtained for the algorithm, had here a log 5 in the exponent, whereas we have just a log factor here and a log cubed before. So, and again, by running, instead of having one MILP, we have K MILPs, where K is so this capital K is the number of types. Yeah, we can just improve the runtime of the algorithm and also simplify it. So at this point, I would like to come to a conclusion. So the main insights of our algorithms were two. First, the use of recursive configurations, and second, a new combinatorial result for integer linear programming. And this result is that given any feasible and bounded integer linear program, where the number with m constraints, which are collected in a constraint matrix A, we are guaranteed to find an optimal solution of small support. And the support size is m times a logarithm in A max, where A max is the largest one norm of any column of A. So it's just, you take all the elements of this column, you add them up, and then you get this one norm, and we have a logarithmic dependence on it. And yeah, I invite you to look at other optimization problems to see if this is bounded and if this can help. And particularly for Makespan minimization, yeah, we use the support bound to get this runtime improvement. We use this idea of recursive configurations to come up with better MILP formulations. And then we used Overdas and other people's work for MILP algorithms to solve it. And just one last comment that I want to make is that if there is a faster MILP solver, which has the same runtime as solving ILPs, then we also obtain a runtime improvement that matches the one for Cmax, so the special case where all the machines have the same speed. So in other words, the main difficulty of matching the runtime for the special case that all machines have is that we need to deal with these fractional variables. So if there's a way to make them integral and just solve an ILP, yeah, then we are in good shape and we can obtain even better runtimes. Yeah, and as I said, we can also extend this to other related or more complex scheduling models, which is nice because it shows a certain robustness of the techniques that we have here. And especially that it's simpler should make the paper also appealing to read. And I invite you to read the paper, which you can find here on the archive. So we put it there last year in May, and it has been published at Isaac last year in Kyoto. And yeah, this concludes everything that I would like to share with you. And now I'm happy to take your questions.
Okay, thank you, Matthias. So everybody should be able to unmute, so please go ahead. So Jan-Karl Lenstra is asking some questions on chat. So if you may go to chat.
Okay, so yeah, the question is there any hope and improvement for Cmax? So so Cmax is the problem where the runtime of any job depends arbitrarily or varies arbitrarily over all the machines. So that's a very good question. So this is a setting which generalizes Cmax. yeah, I don't know how to interpret the word hope. So the point is, so we get an improvement, but only if the number of machine types, so if there's a bound on the number of different machine types. For the general setting, when there can be an arbitrary number of machine types, I have no idea. I would love to see it, but yeah, here, if I go back a slide, you see that unfortunately, we have this k in the exponent. So the number of different machine types, we have that in the exponent. So our approach is not strong enough to solve this. More and new ideas are needed. Yeah.
There is another question from YouTube also. One user is asking if we can go back to define support again.
Yeah. So I don't have a slide where it is, where the support is defined, but I can just say that yeah. So it is the number if you solve an MILP like this, then or let me go back to the slide where the result of Eisenbrand is mentioned. I think this is this one. So the support size is the number of variables that take a non-zero value in the solution. So all the other variables take zero value, and we can simply discard them.
Okay. Any other question?
Hello. Thanks for the talk. I was wondering, did you implement it? And if yes, I have two questions. First of all, for example, how long does it take to process an instance with 20,000 jobs, for example? And secondly, of course, you are aware that multi-fit, which also uses binary search and the first fit decreasing algorithm, which is very simple, is able to produce results of within 3% of the 3% of the optimal schedule, and therefore is and even better if there are many jobs and kind of many machines. I did a study on that. So would it be better than multi-fit, your approach? I understand that it makes epsilon very small, but did you compare the running time, or what do you think? We need to sort the jobs. FFT does need n log n to sort the jobs. So
Yeah.
is that worse than your algorithm because you don't need to sort them?
Yeah, thank you for this question. So no, we haven't implemented it. I know that the special case for Cmax has recently been implemented. It's actually quite non-trivial, and it turns out, so the paper is called The Long Road from Theory to Practice, because it is a long road. It turns out that there is a way to obtain good practical results. So this is a very natural question that you are asking. So with effort and time, I think it should be possible. If the results are then comparable to the ones that you mention, that I have no suspicion or I have no clue if that should work or not. Yeah, that's definitely a good question for future work.
Mm-hmm. So currently multi-fit is the answer, or what? For this problem, I think. Or other.
Yeah, I'm not also aware that the previous algorithms have been implemented for Cmax, or if they have been implemented, because
it's a theoretical answer, and I understand it's a theoretical result. Thank you. Thank you.
Thank you. Any other question? If not, let me thank you, Matthias. Thank you very much, and we have been proud of having you here. And now let me invite you to the next seminar, which will be on June 12th. And Ender Ostsand will talk about machine learning, meeting selection, hyperheuristics. So please be here in 2 weeks, and you will hear about machine learning and hyperheuristics. Okay. Thank you very much for being with us, and see you in 2 weeks. Thank you, Matthias. Bye-bye.
Yeah, thank you. Bye.
Okay, bye-bye.